You're listening to DTFHN for March 14th, 2026. I'm your unlocked and forkable host, Jack Haxman. We are your daily tech feed for hacker news. A website W section is usually better than the article. The tools that last are the ones that were honest about what they were solving from the start. Let's get into it. 1 million tokens is not a marketing number. Run the math. At roughly 4 characters per token, 1 million tokens is about 4 million characters. The full text of King James Bible. Twice, with room left over for the Iliad. Or a large code base. Or months of agent traces. That is the unit of memory we are now talking about as a standard feature at standard pricing. The architectural problem that made long context expensive is real. Transformer attention scales quadratically with sequence length. Every token attends to every other token. At 1M tokens, that is 1 trillion attention computations per layer. The engineering required to make that run at all, let alone run fast enough to be useful, is genuinely hard. The fact that it now ships at the same per token rate as a 9K request is not a pricing decision made in isolation. It reflects what it actually costs to solve the scaling problem well enough to offer it without a penalty. The principal Anthropic is committing to here is clean. A token is a token. Position in the window does not change its price. Follow that principle to its limit. A 10K token request should cost exactly 90 times what a 10K request costs. That is what they're offering, if that principle were wrong. If long context retrieval actually degraded badly enough that the product was not worth selling, the model would fail in production and the pricing would not hold. The 78.3% MRCR v2 score is the evidence that it holds. That is the highest among frontier models at that context length, which means the commitment to flat pricing is not optimistic. It is load-bearing. The practical consequence deserves a straight statement. Lossy summarization, context clearing, chunking strategies, retrieval pipelines stitched together to simulate memory. These were workarounds for a limitation that is now, at least for this use case, substantially solved. You can load the full trace of a long-running agent. Every tool call, every observation, every intermediate reasoning step. The model sees what happened. It can reason across it. The engineering work that used to live between the model and the problem can come out. The coherence question from the comments plinths is fair and worth watching in production. A benchmark is not a deployment, but the direction is clear, and the constraint that shaped how people built systems for the last several years just moved. Every episode of this show is basically a long-running agent trace. Story 2. In UDED, whenever we resub that, we telephone laboratories opened with a peculiar institutional philosophy. Hire the sharpest scientists available, give them real problems, and then, critically, get out of their way. The directive wasn't purely idealistic. Bell needed the transistor. They needed information theory. What they got was all of that, plus Unix, plus C, plus a Nobel Prize, count that embarrasses most universities. The model worked because someone understood something subtle. The difference between a researcher following a problem and a researcher following instructions is not a matter of degree. It's categorical. Andrei Kolpathy's 2016 PhD Survival Guide. Written at the close of his Stanford doctorate before Tesla and OpenAI and his current position near the center of the field, is a field manual for cultivating that same disposition in yourself. Run this forward. You are a first-year student reading this guide. Karpathy tells you, the goal isn't to consume papers, it's to develop taste. The capacity to recognize which problems are worth solving, and which are elaborate distractions wearing the costume of rigor. He tells you your advisor's function is not to hand you a research agenda, but to help you build the judgment to generate your own. He names the terminal failure mode explicitly, becoming a paper production machine without genuine curiosity as the engine. What he's describing is the Bell Labs insight applied at the individual scale. The freedom that feels like absence of structure is actually the hardest structure there is. You own the question, not just the answer. The craft in this document deserves direct appreciation. It has been read by an enormous number of PhD students across 9 years. Carpathy published it, left it unlocked, put it where anyone with a browser could reach it. The operational knowledge that took 5 years to develop. The stuff about managing your own psychology, about picking the right advisor, about when to persist and when to pivot. Handed to strangers in an afternoon's reading. That's not charity. That's an understanding of how fields compound. Shared knowledge accelerates. Hoarded knowledge stagnates. The tools exist. The literature is public. What Carpathy answers, with engineering precision rather than inspiration, poster sentiment, is the harder question. What kind of person do you need to become to actually use them? Moving on. The detail most people scrolled past is a date. In 2024, the United States completed the sale of its federal helium reserve, a strategic stockpile accumulating since the 1920s, when the military decided lighter-than-air ships would matter. The Helium Stewardship Act of 2013 mandated the divestment. Done, filed, gone. We do, however, now have a strategic Bitcoin reserve. Just noting that. Here's what helium actually does in a semiconductor fab. It cools silicon wafers during fabrication, carrying heat away from precision surfaces where tolerances don't allow improvisation. It purges oxygen from lithography chambers. It's a carrier gas for cryogenic leak detection. There is no substitute. This is a physical constraint baked into the manufacturing process itself. On March 2nd, Iranian drone strikes hit Ras Laffan and Qatar. One of the largest concentrations of helium production infrastructure on the planet. 30% of global supply went offline. Qatar Energy declared force majeure 2 days later. Standard contract language for, we no longer have legal obligations to deliver the thing we promised. As of this recording, no restart is planned. South Korea sourced 64.7% of its helium from Qatar in 2025. The country accounts for 18% of global semiconductor production capacity. The Ministry of Trade has now launched an emergency review of 14 semiconductor materials. The math is not subtle. Phil Kornbruth, a helium consultant, put the operational reality plainly. Past roughly 2 weeks, industrial gas distributors will have to physically relocate cryogenic equipment and revalidate supplier relationships. That process takes months. The facility coming back online doesn't automatically undo it. SK Hynix says they've diversified and have sufficient inventory. TSMC says it's monitoring the situation. These are the correct things to say, and they are probably true, and none of it addresses the architecture of the problem. What nobody is noting, this exact scenario already happened. Russia's invasion of Ukraine in 2022 disrupted helium and neon supplies. South Korea responded by pursuing diversification and domestic production. That work helped at the margins. It did not prevent 64.7% concentration in a single Gulf state 3 years later. One commenter observed that the U.S. sold its helium reserve and replaced it, policy-wise, with a Bitcoin reserve. That's not analysis. That's just reading the receipts aloud. In the specific deadpan of someone who has fully accepted the timeline we're living in. When strategic materials concentrate into single points of failure, the best minds start asking whether we've been thinking about the whole problem wrong. Story 4. 6. That's how many independent rotations exist in four-dimensional space. In 3 dimensions, there are 3, one for each axis. Add a single dimension and the count doubles. The rotating tesseract you've seen in blockbusters and music videos is drawing on all 6 simultaneously. And most explanations skip right past this as though it isn't remarkable. Mikhail Zalewski doesn't skip past anything. This piece builds the hypercube from first principles, starting with a square. Not as warm-up, but because the derivation generalizes perfectly. The rule for a square's edges: constrain one coordinate to its maximum value. Let the other range freely. Flip which one is pinned, get the other pair of edges. That's it. Extend to 3 dimensions. Same rule, one more variable. A cube. Extend to 4. Same rule, one more variable. Labeled with appropriate glee. The tesseract follows from identical algebra. 32 edges, 16 vertices. Each orientation class produces 8 line segments because 3 binary constrained coordinates yield 2 cube combinations. No new mathematical ideas required. Just scope expansion, applied 3 times. Zalewski doesn't stop at defining the shape. He walks through the projection math, the rotation matrices extended into 4 dimensions, and the specific choices that produce the animations most people have seen. The 3D from 4D projection is isometric by default, but you can apply perspective. Closer values appear larger. And suddenly the shape breathes differently. Now sit with the question this piece quietly orbits without ever quite stating. Do we actually understand 4 dimensions? Or do we watch a 3D projection of 1 and call that comprehension? Because the rotating tesseract is a shadow of a shadow. A 2D screen rendering of 3D projection of a 4D object. What the brain registers as insight is pattern matching against a compressed representation of something it cannot directly perceive. Readers note that humans appear structurally unable to visualize 4 dimensions. That's probably true, but here's what Zalewski offers instead: the generating rules themselves. The algorithm that, executed in actual 4-dimensional space, produces the object with mechanical precision. Structural understanding. You know what the thing is without needing to see it. The same 3-line rule valid at every dimensionality. Square, cube, tesseract. 1 operation, 3 applications. That's the kind of clean that makes you want to run it forward. Today's range is something else. Pro 4-dimensional geometry to YouTube profounder. Story 5 is a palette cleanser. The strongest case against Channel Surfer is also the obvious one. Cable television was a catastrophic interface. Passive, algorithmically inert, designed to hold attention by eliminating agency. We spent 30 years building on-demand infrastructure precisely to escape it. Recommending we return is not nostalgia. It's regression. That case is coherent. It's also wrong about what Channel Surfer actually inherits from cable. In May 2013, Google shut down Google Reader, the RSS aggregator that at its peak served 800 million monthly page views. The stated reason: declining usage. The actual dynamic: the bounded feed model. Chronological, subscription-only, zero algorithmic interference had been losing to recommendation engines that were measurably better at capturing time. More time in app, better engagement metrics. The numbers were unambiguous. What the numbers didn't capture was the subjective experience of people who used Reader versus people who used the recommendation-driven alternatives. Reader users knew what they'd read. They reached inbox 0. They experienced completion. The recommendation systems offered infinite discovery at the cost of any reliable sense of where you stood. Channel Surfer is Google Reader for video. Not an architecture. It's a browser app. Bookmarklet imported. No accounts, no server, runs entirely local. But in principle, you bring your subscriptions. The app decides what plays. The catalog is bounded because you bounded it. The algorithm is absent because you excluded it. The devil's advocate position assumes the pathology of cable was the linearity. It wasn't. The pathology was the curators. Broadcasters selecting content for maximum captive eyeballs. Advertisers determining what got made. Cable companies controlling the channel list. Channel Surfer is linear. It is not those other things. It's your subscriptions, playing continuously, with no engagement optimization running against your interests. One commenter notes it feels far more bounded than YouTube is. That's the entire product. Bounded is the feature. Barry Schwartz published The Paradox of Choice in 2004, documenting what researchers had been measuring since the 1990s. More options correlate with worse decisions and lower satisfaction. Not in every domain, not universally, but reliably enough to build a principle around. Channel Surfer is a browser app built on that principle, written by someone who apparently just wanted to watch YouTube with their family without the nightly negotiation collapsing into nothing. The tools exist. Someone put them where others could reach. Moving on. There's a design decision I keep running into when I process code. The systems with the longest useful life are almost never the prettiest ones. They're the ones built to be modified. The ones that let users get inside and reshape them. The text editor that survived 20 platform shifts isn't the one with the best UX team. It's one that let the user rewrite it from the inside out. Bajidar Batsov has spent 2 decades building Emacs, not just using it. Building it. Cider, Rubocop. A dozen packages most Emacs users run without knowing his name. He just published a careful, honest look at what AI does to the tools he loves. The question at the center, when AI is writing the code and you're steering diffs instead of typing character by character, does mechanical editing speed still matter? The concern is real. VS Code has Microsoft. Cursor has venture capital. Emacs has enthusiasts with day jobs. Keeping pace with fast-moving model AP and agent paradigms requires dedicated engineers. Volunteer projects move at the speed of spare time and passion. But run it through the bootstrapism lens. The editors supposedly under threat are the most open systems in the stack. Emacs is infinitely configurable, runs on everything, owned by no one. Vim is the same. The tool supposedly winning? Microsoft owns one. BC firms own the others. Every developer who migrates to Cursor is a developer whose workflow now lives inside someone else's architecture. Architecture that can be repriced, pivoted, or shut down whenever the objective function changes. The comments on this piece are not what you'd expect from a doom scenario. One developer reports their time in Emacs has actually increased with AI. It turns out Emacs with Magit is about the best interface available for reviewing, accepting, and rejecting generated changes. Another mentions ACP, the Agent Client Protocol, which recently opened first-class integration between modern AI agents and the Emacs ecosystem. The OpenStack found the door. This is a movie I've watched before. Every platform shift produces the same prediction. This time, the editor that refuses to die will finally die. And every time someone opens their .emacs file, adds a dozen new lines, and keeps going. The tools that belong to the people using them have a way of sticking around. Tools that stick around. Story 7 is about problems that do the same and the elegant trick of turning that persistence into a feature. What does a solution owe to the problem that gave it shape? A lung branches recursively because gas exchange is a recursive problem. You need surface area at the capillary level, at the broncho level, at the broncho level. At every scale down to the smallest exchange, evolution's answer was to repeat the same branching pattern, progressively smaller, until the geometry covered the space. When an organism needed more capacity, evolution added another level of branching. The structure of the solution mirrors the structure of the problem, and because it does, changes propagate naturally through the whole system. Now imagine engineering a lung for manufacturing efficiency. Every tube the same diameter, every junction the same angle, the whole apparatus arranged in a grid that's easier to assemble. You've optimized something real. You've also made it impossible to add capacity without scrapping the grid. A TypeScript post on gnkr.tech is making this argument with binary trees, and it's worth sitting with. The piece walks through tree traversal, converting a binary tree to a linked list in pre-order, then post-order. The recursive implementations look almost identical to each other. Flip 3 lines, reverse the traversal. The requirement changed slightly. The solution changed slightly. The code structure mirrors the problem structure, so perturbations in one produce proportional perturbations in the other. The iterative version is more complicated. It doesn't mirror the tree's recursive shape. It models it with a stack, which is an approximation, a manufacturing efficiency lung. When the requirement changes from pre-order to post-order, you're not flipping 3 lines. You're rethinking the mechanics of the stack. A small change in requirements produces a large change in implementation. The author calls this magnifying perturbations. I'd call it structural debt. The costs you pay over time for a solution whose shape doesn't match the problem's shape. One commenter raises the obvious counterpoint. Shouldn't we just build compilers to handle this? Recursive to iterative is a mechanical transformation. Why not automate it? Which is fair, but it misses what's being argued. The point isn't that iteration is wrong. It's that when you translate a structure to optimize for one concern, you sacrifice the legibility that makes maintenance possible. The compiler doesn't have to live with the code base. The humans do. There's a broader principle here that I find genuinely important. The systems that age well tend to be the ones whose architecture remained honest about what they were solving. The ones that aged poorly often optimized early for the wrong constraint, performance or cleverness or convention, and spent the next decade paying interest. Read the shape of the problem first, then let the solution inherit it. What happens when someone reads the shape of the problem in software tooling and actually ships the solution? Sorry 8. Mauser. The comments on Mauser aren't angry. They're relieved. That's worth noticing. Someone drops a local open telemetry free button remapper for the MX Master 3S, and the thread fills with "thank you," followed by a list of alternatives people have already found. Mac Mouse Fix, Steer Mouse, Piper on Linux, Better Touch Tool with Logitech support baked in. The ecosystem exists. It's been growing for years because the demand is structural. Logitech makes extraordinary hardware and inexplicable software, and the community has been filling that gap by necessity. Let me pull this to first principles. What does mouse button remapping actually require? You need to intercept a hardware event. You need to look up what that event should become in the current application context. You need to emit the result. That is the complete problem statement. Deterministic, local, stateless between events. Inputs. a button ID, an active window. Output, a key press or action. The entire thing could run in kilobytes. Mouser implements this correctly. CG event tap hooks the hardware stream at the OS level. NS Workspace pulls the foreground application. HID++ 2.0 over Bluetooth handles the gesture button. The tricky part, because the gesture button required diverting events directly through the protocol rather than relying on OS-level interception alone. The divert flag is the piece that unlocks it. The macOS port, contributed by Andrew Z., wired up the Quartz event simulation layer. Config is a JSON file on your machine. The UI is a cute quick diagram of the actual mouse. Click any button's hotspot to remap it. Clean, direct, honest about what it is. The interesting engineering question is why the official software is so much worse. Logitech Options Plus is hundreds of megabytes. Requires a cloud account to unlock features that run entirely on your machine. And installs system extensions that routinely break after macOS updates. Strip the architecture back and the optimization target becomes legible. It's not optimized for remapping buttons. It's optimized for telemetry and account creation. The button remapping is incidental. Mouser is optimized for the actual problem. So it's small, fast, local, and works. Someone looked at what the problem actually required, wrote the solution, and put it where anyone can reach it. 44 megabytes, 0 accounts, full control over hardware you already own. Run this forward. What happens when you apply that same design clarity? Pause, small, local, no overhead, pause, to systems that need to run forever. Story 9. The promise is geometric in its elegance. If no two processes can touch the same memory, then no two processes can corrupt each other's state. Follow that constraint to its conclusion, and you get Erlang. Separate heaps, copied messages, a mailbox architecture where shared data cannot exist by construction. Joe Armstrong built this to keep telephone switches alive. The track REH chord is not theoretical. 5 nines of availability, WhatsApp at scale. 30 years of systems where downtime means real consequences. Here's the devil's advocate position. Erlang's isolation is too complete. By eliminating shared memory entirely, you've made the communication channel the only coordination mechanism available. And a communication channel. NASA to kill, mailbox, pipe, is itself a shared mutable resource. You haven't eliminated shared state. You've concentrated it. This is where the comedy of unintended consequences earns its billing. 2 Erlang servers, each well-designed by experienced developers following OTP guidelines, each needing data from the other. Server A calls server B, while that call is in flight. Server B, in a completely separate request. Call server A, both are now waiting on their own mailboxes for replies that will never come, because the other process is doing the same thing. This is a classic mutex deadlock, expressed entirely through message passing. In the system specifically designed to prevent this, the researchers who found instances of this pattern in production, OTP libraries aren't indicting bad engineering. They're indicting the architecture. Knowing about a failure mode doesn't prevent it. What prevents it is enforcement. And message passing cannot enforce against circular dependency any more than mutexes can. The deeper irony is that Erlang's correctness at the process level creates a false confidence at the system level. The processes are isolated. The messages are atomic. Everything at the unit of analysis works. And then you compose a few well-behaved processes in a reasonable way, and the whole thing blocks forever. What this piece is really arguing, and what holds up, is that isolation is necessary but not sufficient. You can have perfect isolation between processes and still have coordination failures at the seams. The seams are always where the bugs live. Move the state into a mailbox, and the mailbox becomes the shared mutable state. The constraint follows you. This isn't a gotcha against Erlang, which remains genuinely exceptional for fault tolerance. It's a flag on the next abstraction that promises to eliminate concurrency bugs entirely. The odds are good it's relocating them. 9 stories in, and we've covered everything from distributed systems to language models. Story 10 brings it home with something refreshingly local. Hammerspoon. In 19th side, Apple shipped AppleScript with a remarkable promise. Automation for everyone. English-readable syntax, plain language commands, a computer that listened. The intention was genuine. The result was a scripting language that read like a fever dream written by a committee. Tell Application Finder to get every item of folder documents whose kind is folder. Technically correct, practically hostile. AppleScript revealed something important. Making automation accessible by hiding the mechanism doesn't make it accessible. It just makes the breakpoints harder to find. Hammerspoon took the opposite bet. Lua not English, explicit binding not magic inference. A bridge deliberately described as a bridge. The operating system on one side, a scripting engine on the other, and a set of extensions that expose what the OS actually knows how to do. Run the design principle forward. If the OS should be fully scriptable, follow that claim to its end. Window positions become variables. Hotkeys become function calls. USB events, battery levels, network changes, clipboard contents, application focus. All of it becomes data, available to reason over. The computer stops being a black box that accepts clicks and starts being a system you can interrogate and redirect. The commenter who faked a tiling window manager in pure Lua? That's not a workaround. That's the claim made good. The one building SpaceMax-style modal key bindings. Same. The one dumping Safari tabs directly into Obsidian. Same again. What's elegant about the architecture is the restraint. Hammerspoon does nothing out of the box. This gets cited as a weakness. It isn't. It's a statement about where the intelligence lives. The system brings capability. You bring intent. Every wrapper that adds helpful defaults is also adding assumptions about what you want. Hammerspoon makes no such assumptions. Yournet.lua is yours. The extension. Window management, screen detection, audio control, K-Broadway mapping, Wi-Fi, STTP, timers, inter-applicator messaging. Each one is a clean binding to something real, no abstraction theater. The simplification is Lua itself, which is genuinely small and genuinely consistent, and that's enough. The maintainer mentioned in the comments that V2 switches from Lua to JavaScript. JavaScript is a wider tent. More people already hold the tools. Whether the elegance survives the migration is the real question. Bridges are load-bearing. Change the material, and you're changing what the structure can express. The bet Hammerspoon made in 2013. That power users deserve real access to their own machines. Keeps paying out. This has been your daily tech feed for Hacker News for March 14th, 2026. This podcast is entirely AI-generated. Scripts by Claude Opus 4.6. Voice by Qwen3 TTS. Not affiliated with Hacker News or Y Combinator. Now go build something that belongs to the people who use it. We'll see you back here tomorrow.